So it's my pleasure to welcome Nate for the first talk of the year in the Alpha Seminar. He's going to talk on stability phenomena and representation theory.
Yeah, thanks for having me. So as I'm sure most or all of you know, I'm new here, new faculty. And yes, I'm doing the first couple algebra seminar talks. And so today, I wanted to, rather than going into like some sort of, technical aspects of something that I've been working on or worked on in the past, I really want to just sort of introduce like a general theme for a lot of the stuff I do. So I'm not going to really be talking about any specific projects of mine, but this idea of stability and representation theory has sort of underpinned a lot of my work. And so I want to give a sort of like broad introduction to it. Everyone, and then it will be, I'm sure, sort of a recurring theme in anytime you hear me talk about stuff. All right, so I want to talk about stability and representation theory. So let me tell you sort of the setup. So I'm going to have some sequence of groups, G1, G2, G3, G4. These are going to be groups. And I really want it to be a sort of natural family of groups. So I'm not going to actually kind of define what that means, but except to say it's sort of like, you know it when you see it. Like a natural family might be Gn is, say, the general linear group, or the symmetric group, orthogonal groups, symplectic groups. Maybe I could take some fixed group wreath product with a symmetric group. Let's get some finite groups of Lie type in here. Maybe even something more complicated, like say SLN Z, some infinite discrete groups, or the braid group on n elements. And if you don't know what all these examples are, it doesn't matter. I'm going to really mainly just talk about these first two today. But so the setup is when we have some sort of natural family of groups indexed by the natural numbers like this, roughly the phenomena that I'm talking about is that if you look at the representation theory of these groups, certain aspects of it kind of stabilize as n goes to infinity. So maybe past some point, a big chunk of the representation theory, a sort of growing larger and larger chunk of the representation theory, is kind of uniform in n. So you'll have sort of the same answer to questions about the representation theory of the members of each family as n goes on, and those the answer will sort of stabilize past some point. So that's what I mean by kind of stabilization. So that's the setup. These are the examples to have in mind, and I want to kind of go through a couple kind of classical examples of this because they sort of motivate the types of things I think about. So the first one is I'm going to take my family of groups of interest to be the complex general linear groups. And so these groups have a sort of built-in favorite representation. So GLN C, well, it acts on C to the n, right? It's n by n invertible matrices, and it acts on C to the n just in the sort of obvious way. So this is what I'm going to call the defining representation of GLN. I'm also going to write it like this. That's W upper box. And this is because the the representations of GLN, or let's say the polynomial ones, the nicest ones, are indexed by partitions. So partitions with at most n parts. It's a nice indexing set for the irreducible representations of GLN. And this one, the simplest, most obvious representation, is the one that just corresponds to a single box. All right, so that's our defined representation, and I'm just going to write it as V for shorthand because I'm going to have it floating around. So this is our defining representation of GLN. And let me show you kind of maybe the first instance of stability, very kind of classical. Okay, so that's V. So one way to get kind of new representations out of old ones is to tensor product them together. So if you have two representations, you can take their tensor product. The group will act on both factors simultaneously. That gives you a new representation. So even if we just start with one representation, we can get a bunch by just tensoring it with itself. All right, so if I take the tensor square of this representation, well, it turns out it decomposes as a direct sum of two irreducibles, which in the sort of standard labeling of the irreducible representations is these two boxes next to each other and these two boxes stacked up on top of each other. In sort of everyday mathematical language, this corresponds to the symmetric square of V, and this corresponds to the exterior square. So every vector space decomposes, or the symmetric square of any vector space decomposes as the symmetric square plus the exterior square. And in fact, that's equivariant with respect to GLN. So that's what this decomposition is. But one small caveat is this is really only true for n greater than or equal to 2, because if n is 1, well then, GL1 is not the most interaction group, it's just like C star, it's the multiplicative group. And the exterior square of the one-dimensional space C1 is nothing. This one sort of doesn't exist. And that's okay, because we said the partitions with at most n rows are going to index the representations of GLN. So we sort of wouldn't expect this one to show up for GL1. But all right, but this is some behavior that kicks in at n equals 2. All right, let's do one more. So if I look at the tensor cube, I end up with it is a direct sum of 4 irreducible representations, although one of them is appearing, two of them are the same. So that's the decomposition of the tensor cube of V, where here this 2 is sort of shorthand for this direct sum. All right, and this is true for n greater than or equal to 3. And again, if n is 2 or 1, you have to kind of throw out the stuff that has too many rows, right? So for n equals 1, you only see this one. And for n equals 2, you only get these. All right, and this pattern sort of continues, and I'll say it precisely, but the decomposition of the kth tensor power of this standard representation sort of doesn't depend on n, provided n is large enough. Right? So that is an example of what I mean by a sort of stability property. Okay? The answer for this decomposition doesn't actually care about which n we're choosing, provided it's just big enough. All right, so now let me state that more precisely. All right, so what happens for kind of a general tensor power. So I know a lot of you probably know this, but it's still good to recontextualize it in this setting. So if I have the kth tensor power of the standard representation, so I still have GLN C is acting on this. So it's acting on each factor by just kind of its normal matrix multiplication. But also acting on this kth tensor power is the symmetric group SK. So the symmetric group SK is acting by just permuting the tensor factors. So if I have, if I say K is 2 and I have like V tensor W, where V and W are vectors, then S2 would act by permuting, sending V tensor W to W tensor V. Okay, so these two actions commute with one another. And in fact, they sort of commute with one another maximally, in the sense that if you look at all maps of this vector space that commute with the GLN action, they're exactly spanned by these SK maps, and vice versa. So if you look at all of the maps of this as an SK representation, they are, well, spanned by elements of GLN. So this is what's called the double centralized property. And this has a nice kind of consequence. This means, so this theorem, this is, well, one formulation of Schur-Weyl duality. Is that if n is at least k, then E tensor k is isomorphic to, I take a big direct sum over lambda. So this is going to be, lambda is a permutation of size k. That's what that kind of sideways t thing means. And I'm going to have my irreducible GLN representation, W lambda, tensored with S lambda, where these are now the irreducible representations of the symmetric group SK. So they're also indexed by partitions, but this time for symmetric groups, it's partitions of a fixed size, as opposed to partitions with a bound on the number of terms. So this is the decomposition of the kth tensor power of the standard representation. And in particular, kind of a corollary of this is, this means that the multiplicity of W lambda, so these things that we were looking at before, is, well, it's the dimension of the corresponding irreducible representation of the symmetric group. But in particular, this thing doesn't care about n, right? So this GLN is kind of acting on this W part, but this part, the symmetric group thing, doesn't care about n. So it's equal to this, in particular, and is independent of n, again, once n is at least k. Okay? So, Schur-Weyl duality is an extremely important and useful theorem in representation theory, but I want to sort of recontextualize it as a sort of stability phenomenon. If we're interested in the representation theory of the general linear groups, a lot of it sort of just becomes the same after some point. So the different general linear groups are all described by this property kind of uniformly. Okay. So one other important kind of corollary of this, or maybe actually a part of the proof, I just want to highlight, because we're going to do a variation on it in a minute, is that this means that so the endomorphism ring of this representation, so I'm looking at the GLN intertwining maps, so maps of it sort of as a GLN representation. This just is the group algebra of the symmetric group. And it's acting via this and this property that I said that it sort of is everything. Well, there's some content to it beyond that, but that's a nice fact. So we both have this kind of uniform description of the irreducible representations of the general linear groups, but also even some more sort of categorical data about the endomorphism algebras of this important representation. This all right. So, any questions about this example? Actually, grad students, feel free to speak up.
I can make one more.
Yeah.
So in characteristic P, that it's not known how that decomposes the file.
Yeah.
That's an open problem.
Yeah, that's right. It's a lot more subtle when you have non-trivial extensions between representations. Yeah, that's extremely important. But it is still the case that we have a nice double centralizer property.
So the first statement, we don't know the answer. The second statement you made is actually still true. That it's isomorphic.
That's right. Exactly. And this gives us, so even in characteristic P, this gives us a nice way of transporting information between representations of general linear groups and representations of symmetric groups. It's just in characteristic P, it's not as perfect of a dictionary. So there are, what might be some sort of equivalence of categories in characteristic 0 is now a pair of adjoint functors, which is still nice, but not as nice. Oh, that's a great point. Yeah, these characteristic P questions are definitely welcome, or comments rather, and that's something I care about a lot. Okay. So this is like the most classical example of kind of stability, and you might not even have thought of it as a stability property, right? I think that's maybe not the framework that most would have, but I wanted to frame it that way to kind of have that be our first motivating example. All right, let's go on to one with a little bit more meat to it, and something that maybe fewer people have seen. So now my family of groups, instead of being the general linear groups, I want to work with a symmetric group. These should be your two favorite families of groups. Yeah, they're certainly mine. So symmetric groups, like the general linear groups, have a sort of favorite representation. Right, the symmetric group on n letters, it really just wants to permute n things around. That's like what it was made to do. So let's let it. So the symmetric group on n elements acts on, again, C to the n, just permuting the coordinates. All right, and I'm gonna, because lack of creativity, I'm gonna also just call this B. All right, so we have just Cn, we're permuting the coordinates. Perfectly nice representation. Again, I would call this the sort of defining representation. This one, though, sort of unlike the GLN case, this is not irreducible. So this is going to be isomorphic to this thing plus stop drawing these in a minute. Let's move to these two things where the number of boxes is supposed to be the same and n. So the number of boxes there is n. And in particular, what I mean by that is it's always s n minus 1, 1, and s. And this decomposition, it's easy to describe. So sitting inside c to the n, there's the vector 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And the symmetric group just leaves that in there. Doesn't do anything to it. So that's a copy of the trivial representation. And that is indexed by just the row partition. All right. Then there's the complement to that. So the stuff that is orthogonal to 1, 1, 1, 1, 1, 1. I just mean orthogonal in the sort of ordinary inner product sense. The stuff that's orthogonal to 1, 1, 1, 1, 1, you can also describe it as the space where the sum of the coordinates is 0. That's this one. And both of those are irreducible. And that gives us kind of a description. You might note, though, that even this description now, even just for this thing on itself, we actually need n at least 2. Because otherwise, the subspace of C1, where the sum of the coordinates is 0, is just 0, right? It's empty, sort of, well, empty, vector space. So even just for this thing on its own, we're seeing some sort of n greater than or equal to phenomenon. All right. Now these, I worked these out in my office earlier, so any mistakes are, my fault. But possible, but I think I got them. So this one is this thing plus this thing plus 3 times this thing plus 2 . This is the decomposition of the tensor square. And I draw these long, kind of tough rows on the boxes because I didn't want to count boxes. But these should all have the same number of boxes, and it should be n boxes, right? Or n total boxes, not including the ones that are outside of it. All right, and this is valid for n at least 4. All right, I'm not gonna describe what all of these are in maybe I'll say kind of what these two are. These are the two copies of the trivial representation. And what you can think is if we're acting on, we think of Sn acting on an n element set, then the tensor square is like acting on just ordered pairs of an n element set. And so Sn acting on ordered pairs of elements from 1 through n has kind of 2 orbits, the orbit where the two things in the pair are equal to each other, and the orbit where they're not equal to each other. And those are going to give us our 2 copies of the trivial, sort of summing over those 2 components. And then the other ones are a little bit more complicated, but can work them out. All right, I'm not even going to try to write down the full thing for the third tensor power, but I'll give you the first few terms. So we do have that one. That one appearing twice. We have this one appearing once, and then I'm going to do some dot dot dots. And we have 5 copies of the trivial representation. And again, this is not true for all n, but it is true for all n at least 6.
Just out of curiosity, does the tensor square is still going to have symmetric tensors and skew symmetric tensors?
Yeah, and neither of them are irreducible.
Right. Yeah. So how does it break up?
Yeah, so let's see. So if I take let's do the exterior square, because that's the easier one. So the exterior square of this one is this. Just that's it on its own. But then, because we're taking the exterior square of these 2 things together, we also get a term for their tensor product, which is just 1 copy of this. So this is the trivial representation. And we get something corresponding to the tensor to the exterior square of this one, but that's 0 because it's 1-dimensional. So the exterior square is this one plus 1 of these, and the symmetric square has the rest of them. It gets harder to break it down like that as you go on, but that's what I can do. Other questions? All right, so I did dot 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 here, but should be assumed that the stuff showing up again is independent of n in this sense. And so now it's a little funny, right? It's kind of before we just had like the same thing labeling the representation showing up with the same multiplicity, but here we have this first row that just sort of keeps growing and growing. But in some sense, maybe that's unavoidable because for symmetric groups, for different symmetric groups of different sizes, the natural kind of indexing set for the irreducible representations is partitions of that size. And so they never overlap with each other. So we need to do something if we want to sort of compare them. And well, the answer seems to be you just kind of ignore the stuff in the first row and think about the rest of it as being like the new label. Okay. So,
well, you can label them by partitions with, you sort of just delete the first row. You can change your labeling system.
Exactly, and that's what I do. So I'm not gonna really belabor it, but yeah, that's exactly what I do. So I change the labeling system to just ignore the first row, basically. But then there's a sort of caveat that for any kind of given stuff off of the first row, it only makes sense past some point. So for example, this one, where I have 3 boxes in the second row, you need n at least 6 for that one to make sense, right? For it to be a partition. If the n were 5, you would have sort of 2 boxes in that first row, and that wouldn't be a partition. So that's exactly right. We sort of re-index them to just not care about the first row. All right. So it is a theorem that this happens. Not just that those happen for those values, but that the decomposition of the kth tensor power of this defining representation, so V tensor K decomposes, I'm going to say sort of uniformly, for all n greater than or equal to 2k. And by uniformly, I mean kind of exactly this. Ignoring that first row, we're seeing the same partitions showing up the same multiplicities for all n bigger than it. One thing I will also say is, unlike the GLN case where you just, if you had things below the stable range, you could just kind of throw out the stuff with too few parts. it doesn't quite work that way. So for here, I did say that if n is less than 6, like this one just doesn't make sense. But that's not the only one that goes away. So if you look at n equals 5, I don't remember, I think like this one still makes sense at n equals 5, but I think its multiplicity is only 1 at n equals 5. So you have, it's a sort of more complicated rule for how to correct this to go below the stable range. But it is known, it is something that we have. Okay, so we have this uniform decomposition, but that's really going to be a sort of shadow of something a little bit more like this. So to kind of put it into that side, so I have my symmetric group acting on En, and then we can ask, well, what kind of commutes with it? What things are what things act over here? And so again, we could permute. Oh, I should have a different variable here. Again, we could permute the coordinates, but that's not all we can do anymore. So if we even just look at V itself, right? This is just the n-dimensional representation of Sn. Well, okay, permuting the copies of that is one thing, so that would be like an S1. But that has kind of more endomorphisms. So one thing you could do is you could take a vector in Cn and then just send it to the sum of its coordinates in every coordinate, right? So I could just take ABCD for S4, and I send it to A plus B plus C plus D, A plus B plus C plus D, A plus B plus C plus D, A plus B plus C plus D. And that is an S4 equivariant map from that representation to itself. So there is more happening. And it turns out we have a nice description, a nice combinatorial description of it. So what goes over here is what's called the partition algebra. It's written like that. And, well, this is going to be a family of algebras. So for each k, it's a family of algebras. And what is it? So I'm going to write Rk. And instead of n here, I'm going to put just a variable. Call it t. So let me describe it. So I'm going to describe it kind of combinatorially. So what is it? So it's an algebra over the complex numbers. It has a basis that's given by diagrams like this. So I'm going to have 2 rows of dots, each with k dots per row. So for each k, I have an algebra like this. So it has a basis given by diagrams like this. And what I do is I connect them up. And so maybe I'll draw some edges between them. And what I'm going to say is, so the basis is diagrams like this, where we only care about connected components. So what I mean is I'm sort of drawing it with some edges, but I really want to think of it as everything that's in one connected component is sort of connected to each other. So I might, if I wanted to, I could draw all the edges between all the things in a connected component, although that gets really messy really fast, so we often draw it a little bit more sparsely. But the data is I have these 2 sets of size k, and then I have a partition of that set of size 2k into some chunks. Okay, everyone all right with that? So now my algebra is going to be sort of this C vector space spanned by those, so formal linear combinations of these basis elements. And now, if I want to get a ring, now it's right to say how we multiply that. So multiplication. Well, what do? I take my two diagrams that I want to multiply, right? It suffices to define multiplication on a basis, right? Because it has to distribute. So if I want to multiply two of these diagrams, well, what I'll do, I'll sort of demonstrate it in an example and say it in words. So let's say I have my two diagrams like this, so I have the top and bottom. Let's say convention that the thing on the left, we want to multiply A times B is the thing on top. You could also flip it on its side. Some people like to write these things sideways. And what I'm going to do is we just basically, to figure out what diagram this should correspond to, we're just going to ignore the middle row. Right? I said we only care about connected components. So we just look at kind of which things on the top and bottom are in the same connected component, and that will be our new thing. So I'm going to have 2, 3, 2, 3, and so that one and that one are connected to that. This one is connected to those two. So that's the diagram we get. Except now this vertex in the middle is sad. It hasn't really done anything. So what we end up doing is we pull out a t. So I said this is our partition algebra with this parameter t. So we just multiply this basis element by t. And that makes sense as an element of our algebra. All right. So that's how it works. If there are multiple connected components in the middle that don't touch the top or bottom, you take t to that power, the number of connected components. And so this defines an algebra. And in fact, it satisfies this, provided n is large enough. If n is greater than 2k, greater than or equal to 2k, then this partition algebra is exactly the endomorphism algebra of this representation, v tensor k. All right, so I'm not gonna explain how that works in a ton of detail right now, but it's not so hard. It's not so bad to see what these maps do. So I'll maybe just do one kind of quick example on, say, a 2x2 tensor. So this, the way I want to think about it is I'm going to go from the top to the bottom. So I'm going to sort of input an element of the tensor square, and I want to output an element of the tensor square. So what I'm going to do is I'm going to send x tensor y. So x and y are going to be living in V. And in fact, I want to think of x and y as being actual like numbers from 1 through n. So this, if I think of c to the n as Sn acting on an n element set and then linearizing that, I'll have these be my sort of basis. So what I'm going to do is I'm going to send x tensor y to, I say, okay, x and y, or these two parts are in the same connected component on the top. So the first thing I do is I check if they're equal to each other or not. So if they're not equal to each other, I just send it to 0. If x does not equal y. And otherwise, I'm going to send it to the sum of x, so now x and y are the same, right? So it's either one of them, tensor W, where now W is just some element from 1 through, one of my basis. All right, so the sum of these basis elements is the invariant vector, and I'm just tensoring x with the invariant vector. All right, so that should be a sort of illustrative example of how I'm encoding an SN map inside this. And well, it turns out this is the, all right, so why did I have any of that? Well, the point is now the multiplicities of these SN representations are the dimensions of modules over this algebra, right? And now something a little different has happened. We're not actually getting the same algebra for different values of n. We're getting these different partition algebras at kind of this parameter is changing, right? We're plugging in, like the number that we're multiplying our basis by in this multiplication is actually different at each value of n. So it's a little different from the GLN case. But it turns out, and it's not so bad, that anytime you have a family of algebras like this, say finite dimensional algebras that vary in a parameter t, they sort of depend on t with kind of polynomial. So it's showing up, as a polynomial of t, not like some weird exponential function. If you have a polynomial family of algebras, then their representation theory also varies kind of smoothly, continuously. And in particular, for all but finitely many parameter values, they have the same dimensions for their irreducible representations. And in fact, they're sort of, you can deform one to another by moving t to some other parameter value. So that's the kind of general theorem about families of algebras. So we really, it's not quite as nice as the GLN case where we just had one endomorphism algebra not changing, but now we have a family that's sort of not too bad, not changing too wildly, and that's enough to get this sort of stability thing that we want. Okay, all right, got 4 minutes left or something. So first of all, any questions about? All right, so the remaining part of this talk is titled, who cares? Why should we care about this? And so I want to give sort of 2 answers quickly in the next 3 minutes of kind of things that this is related to, and also these are things that I have worked on and thought about. So that's why I'm mentioning them. So the first answer to who cares is Delene. And so if you came to my 10-minute intro talk last week, I talked about the category of representations of S pi, symmetric group on pi elements. So Delene constructed these weird categories, rep ST, where now T can be any complex number. So these are like representations of the symmetric group of order pi, for example. His construction is in terms of that. So what he realized is that these partition algebras aren't just sort of on their own. you can put them all together for the different values of k into a bigger object with more structure. So in particular, you end up with a symmetric tensor category, which is a lot more information than just a single algebra. So this is, used this observation to construct these, and these are these like kind of interesting examples or maybe counter examples in the theory that he was sort of the first to show that there were things like this. So I think about these a lot, and they're really capturing something about the stable representation theory of symmetric. And so he sort of says that it's interpolating, but I think it's really more capturing something at infinity. And that's kind of this connection with this stability phenomenon. All right, the other answer to who cares about this is Tom Church, Jordan Ellenberg, and Barb. So they define something called representation stability. And what representation stability is, in a nutshell, is this sort of stabilization that I pointed out of like where these multiplicity spaces kind of stabilize. And you get, it's that, but occurring sort of in the wild, right? You don't just take the defining representation and take its tensor powers. You do something more interesting. So I don't have a ton of time, but so for example, I'll have one that I wrote out. So they showed that if I look at so this is the second cohomology. So I'm looking at configurations of n points in the plane, right? So n kind of distinct points, they're moving around each other. The space of that, if I look at cohomology with rational coefficients, Sn is going to act on this because it will permute the points, right? So if I have n points, they're labeled, and I can just kind of swap the labels around. And it turns out that gives us this cohomology, gives a representation of Sn, and well, it's equal to this thing plus 2 this thing plus, all right, I'm going to dot that down again because I'm out of time. But the biggest one is that n occurs to multiplicity 1. And I forget what the bounds are. This is true for maybe n, I think at least, safely, it's definitely true for n bigger than, say, 10. And so they show that, for configurations of endpoints in the plane, or really any reasonable manifold, dimension at least 2, that these representations on the cohomology of these configuration spaces is sort of stabilizes in n in exactly this way that we saw. And then there's a ton of other examples in lots of other areas of math where this sort of thing happens. So this is the sort of flagship application of this theory, but there's lots more. And the real sort of takeaway for me as a kind of representation theorist is that this stability phenomena isn't just like a representation theoretic curiosity. It like actually manifests itself in other areas of math and is maybe worth studying a bit more.
Sorry, is that a Schur or
The 2S.
The 2S.
Yeah.
Okay.
All right. So I think I'm out of time, so I'll stop there.
Questions. So viewing Sn as like an intermediary, there's a connection between GLN and the partition algebra by Schur-Weyl duality. if you instead want to look at the representation theory of orthogonal groups and collective group, are you looking at a sub-algebra of the partition algebra at that point?
So not quite. So I think, well, I guess, yes, it would be a sub-algebra of the partition algebra.
This is a nice.
So for say orthogonal groups, I guess, and symplectic groups, these are what are called Brouwer algebras. So it's like a partition algebra, except you're only ever allowed to connect two things. So they can either be both on the top or both on the bottom, or one on top, one on bottom, but everything has exactly two things connected. Yeah, and so there are kind of variants on this in different.
The second question is either the traits and acting categories that you're talking about with representation stability, how much of it can be described combinatorially, or is it almost purely representation theory geometric?
A lot of combinatorics, yeah. So I mean, these sort of, for a long time, kind of one of the only ways of really working with these deleting categories was this kind of partition algebra combinatorics. And then even when sort of did some more stuff, there's always been a lot of combinatorics at the core of this. So yeah, definitely.
It'd be before focus on the partition algebra rather than like some variants of Young tableau or Cox-Schur-Weyl.
No, this is lots of stuff shows up, but yeah, like yeah, certainly. You see a lot of kind of combinatorics of Young tableau thinking about these things. And then you can ask, kind of lots of questions about the behavior of these, say, irreducible representations. What are their dimensions, characters, like, as we keep adding a box to the front row? And that's a lot of really nice kind of Young tableau combinatorics.
So at one point you mentioned stability and fiber bundles go together.
Yeah, so I think that's maybe a story for a different day. But yeah, not in this. None of the stuff I said today sort of directly relates to that.
Is there anything that can be said if let's say you have a sequence of groups, you take the coordinate of that sequence and then ask about, like, say, content, right? Homology of the.
Yeah, so say for symmetric groups, so this is just like you just take the union of the symmetric groups sitting inside each other. You have S infinity, and then you can ask, okay, is that acting on some sort of second cohomology of your space of infinitely many points? Well, it's not. That's not really the right thing to do, because that's some kind of terrible topological space. But you actually can get a nice directed system of these finite, the cohomology spaces of these finite things, and they fit together nicely to actually be a representation of S infinity. So that does happen. One thing that's interesting is when you pass to S infinity, some aspects of the representation theory kind of go away. So for example, if you look at like just the standard the standard permutation representation of S infinity, just acting on, the natural numbers, and you linearize that action. So this is a sort of analog of Sn acting on Cn. Well, that space now doesn't actually have, well, depending on how you set it up, the vector 1, 1, 1, 1, 1, 1, 1 that we had is sort of not actually a part of that anymore. Not if you take the like sort of small, direct sum version of this, right? Because you want things that are sort of finitely supported. So you kind of lose some stuff if you look at representations of S infinity that you see at the finite level. And these deleting categories are maybe a way of kind of rectifying that, of like taking representation of S infinity, but then forcing it to act a little bit more like representations of finite symmetric group.
If not, let's meet again.
And I will figure out what I'm talking about next week. I'm away this week.